And let me also the thank you for the kind invitation to be a part of this symposium. I can say I'm already learning a lot this morning and had the chance to meet a friend and collaborator who we'd only met over Zoom for years. So this is a great opportunity. I want to acknowledge Raul Rincon, who is kind of the co-author or co-developer of this presentation. Raul's a PhD student at Rice. And what I'm highlighting here today is some of our recent work in applying different machine learning algorithms within the context of regional risk and resilience modeling, and also in particular where some of his work is headed with this in the future. So you saw from the title that we're looking in this context of resilience quantification and resilience modeling. And we all know that certainly it's a buzzword we've heard around a lot, but what does this really imply in terms of those of us in the earthquake engineering domain and how we're trying to leverage our tools to facilitate decision making in the literature, but some common threads with respect to looking at our ability of systems to withstand, adapt to, and recover from stressors like earthquakes or other natural hazards. And we've seen repeated calls for resilience from national academies, from the DoD, from NIST, from the EPA, including those that proclaim disaster resilience as an imperative for our nation. And it imposes, I think, a heightened bar for us that are looking at risk quantification from natural hazards. In particular, that we're not only quantifying or characterizing the infrastructure and its exposure to these natural hazard events and predicting damage and different measures of performance. We've been very familiar with these notions from performance-based earthquake engineering for decades. It also reminds us of the importance of how this has ties to restoration and recovery modeling and the interdependence of our built environment with other systems, for example, like social and economic systems. And for those of us who like to be able to provide tools to help support risk-informed decision-making, this heightens demands in terms of identifying, quantifying, and propagating different sources of uncertainty through this whole risk assessment. And I think that makes some of the problems that we face in risk and resilience modeling across communities or across spatially distributed portfolios really ripe for some applications from AI and machine learning. And I'll go through a couple of those characteristics in the next few slides. One is that we're looking at these diverse heterogeneous systems that cut across different scales. And you'll see that a lot of the examples that I draw are from the bridge engineering through the transportation and intermodal transportation systems domain. And we see that here in this example. So we want to be able to characterize the performance of our structures, like our bridges and their interacting components, but also recognize that as these structural systems exist within our communities, we have different combinations of these components. And they may be exposed to different hazards across structural portfolios with variations in design details of geometry and so forth. And then as we collect them into infrastructure networks, we need to look at not only how they're topologically connected, but in terms of their functionality and the flow or the services that they support throughout our communities. And you see the example here of the intermodal transportation networks, where we also may be interested in looking at questions that cut across different scales or that require our models to be capable of looking at different scales. For example, we may zoom in to a region, like an example I'll show you much later in the presentation, that's in Memphis. But if we really want to look at goods flow that are disrupted through, say, a railway network, although the footprint of the hazard may be more local, the disruptions may be far cascading, or we may have rerouting across a nationwide network. And this really poses some challenges to our risk and resilience modeling. Other characteristics of these problems that I think could be ripe for the machine learning applications are tied to some of the computational complexity. And we heard a little bit about that this morning as well. Just showing a range of different past examples of where this has been leveraged to avert some of the computational complexity in the past, especially when we're looking at, for example, bridges and with soil structure interaction or liquefaction potential, as we've heard about in the morning, or if we're looking beyond response prediction and looking at things like recovery and restoration modeling with different diverse data sources that may inform it. And so we'll look at some examples from these domains today. And then a last characteristic that I think makes these problems ripe for AI and machine learning is that, fortunately or unfortunately, they're laden with different sources of uncertainty. And you can make that claim from the characterization of the hazard all the way through the structural characterization and response modeling, particularly when we're looking at not only damage potential, but other cascading consequences, such as restoration and impairment of things like connectivity between socially vulnerable populations and critical facilities. Along all stages of this process, we want to be cognizant of this and see how we can capture and propagate those sources. So I think these types of problems provide an opportunity for us to benefit from some of the capabilities of machine learning. In particular, some of the three opportunities that I see would be for the surrogate modeling, and we saw some examples of that earlier, and probably most of the examples I'll show you today draw from that domain as well. Also, synthesizing information from different data sources. And we'll look at an example in the restoration modeling domain where perhaps we may, for example, use empirical data, but also expert opinion data, or you might also consider simulated data. And I think these tools also allow us to be careful about that treatment of uncertainty. To be frank, they introduce additional sources of uncertainty with respect to modeling uncertainty, but also some of the efficiency can allow us to be smart about the way we propagate other sources as well. So today we'll take a look at some past and recent examples of applications of machine learning, particularly in that domain of fragility modeling and restoration modeling that fall within the larger picture of resilience quantification. And then I'll talk to you briefly about some of our ongoing research and opportunities that I see in this space. You may have seen a review paper, and I think it was mentioned in an earlier talk that we published a couple of years ago. It's essentially a review of applications of AI and machine learning in the earthquake engineering domain. And I'll be the first to admit that this paper is already quite out of date, even though it's just a couple of years old. There's been a lot of activity in this space. And it certainly wasn't comprehensive, but it highlighted a few different areas where we had seen machine learning pervasive in the earthquake engineering domain. I want to acknowledge Tim Shih, who led this effort. He's now an assistant professor at McGill. And through some of that work, looked at things like how machine learning had been used in seismic hazard analysis and system ID or damage detection, fragility modeling of structures and other systems, as well as within the controls domain. And the examples that I'm going to present today primarily come out of one of those four areas, in part because that's really the space that we work in. I'm a structural engineer by training with interest in these broader kind of portfolio level risk modeling studies. One of the figures from that paper that I wanted to pull that I think has helped me to start to try to sort out the different types of models and how we might characterize some of the different types of algorithms that we find in the machine learning domain are shown up here. And I'll be pulling examples that cut across, but primarily they fall within that supervised learning category where we leverage labeled data primarily for either classification or regression type problems. And you'll see a couple of examples where we also leverage clustering to try to guide some of this as well. What frankly, I don't have examples today to cover are some of the dimensionality reduction examples. You might see some of the PCA work and some of that seismic hazard characterization work. We've used it some to look at failure surface visualization for some structural reliability problems. But in terms of some of the supervised machine learning algorithms where they've primarily been leveraged in our work, and those of some of our colleagues are for surrogate models of structural response. So you see an example here where perhaps our quest is to develop those fragility models, that statement of conditional failure probability given, say, some intensity measure of the ground motion. We often leverage some sort of computational model, a finite element model, maybe an open seas model, something that would allow us to predict behavior as we vary different input parameters, including the ground motion that the structure is exposed to, but also vary the structural or design details. This is really the place where surrogate modeling, specifically different machine learning algorithms, have been very prominent in our field, are to avert some of the computational complexities of these models, but also to drive some discovery in terms of different predictors that we might consider beyond just, say, a ground motion intensity measure that could inform the shift towards parameterized fragility functions as opposed to univariate. And we'll come back to that concept. And I want to highlight that I don't feel this is a huge departure from where we have come in terms of building fragility modeling. So I think it's fair for us to be very cautious and skeptical of the algorithm that we adopt for these surrogate models. But in terms of the nature of how they affect our fragility modeling, it's not a huge departure. We have been doing this for decades. We refer to them as probabilistic seismic demand models. They may have had much simpler functional forms like the classic power law form with an assumption of a log normal dispersion of demands given an intensity measure. We're starting to relax some of those assumptions, and we're starting to introduce models that perhaps afford more flexibility in terms of capturing the behavior of these systems. So on the top is kind of walking through some of our traditional approaches of designing a statistical experiment, meaning we're sampling on all of these random variables. We're conducting our finite element model. We're developing a probabilistic seismic demand model that characterizes the response given, say, an intensity measure of the ground motion. And we either use that model in closed form and convolve it with a capacity estimate, or in some sampling strategy to compare it to a capacity limit state to ultimately arrive at our fragility function. And we see on the right kind of this classic univariate fragility function. So damage given some ground motion intensity measure. The main change or the main shift that's been introduced for quite a few years now is replacing again that finite element model or the use of the finite element model to inform a PSDM. And now we're informing some form of a surrogate, some machine learning algorithm that we again leverage now in this case, not in closed form, but that we can sample upon to compare to, say, capacity estimates and then arrive at some form of a fragility function. The one I show on the right happens to use logistic regression. We talked a little bit about that in the morning. That doesn't have to be the form of the final fragility, but that is what you'll see in some of the examples that I've shown. And again, we have a generic meta model training shown here, and that's where perhaps some of the effort really goes into comparing different machine learning algorithms that may be appropriate for our structure and set of loading conditions to allow this efficient fragility estimation. I think the other key comparison, besides replacing a classic PSDM with a meta model from machine learning, is what we're afforded on that right-hand side. So now you see that we don't just have damage conditioned on IM. It can be conditioned on ground motion intensity and other predictors, X or P, perhaps as it's noted here. That may be things like geometry of our structure or material properties. And I think this is really an important step forward for us. So I don't want to spend, and I don't want you to ask me a whole lot of questions on this slide, but what I want to state is that we, not just our group, but our field has been doing this type of work for over a decade at this point in terms of looking at comparing different statistical models or different machine learning algorithms that will allow us to efficiently estimate the response of these structures, informed by ground motion intensity measures and different parameters, where we've been leveraging different machine learning algorithms to provide that surrogate for demand estimation. Here is one work that Jay Gosh produced looking at bridge structures and comparing different models with respect to various goodness of fit measures, adjusted R square, a root mean squared error, and a symmetric mean absolute percent error. And what you can see on those spider or radar plots on the right is just a comparison of those different models across different components. So in this case, we're not predicting just one response quantity like column curvature ductility demands, but also things like bearing deformations, for example, or displacements at abutments and so forth. The main outcome of these types of studies is to guide the potential selection of different surrogate models that can be used within a framework for constructing these parameterized fragility functions. So these allow us to explore the impact of different parameters on the failure probability. What if analyses? What if we were to change the connection details? Or what if we were to change the geometry of the structure, the height of the columns, and so forth? How does that influence our failure probability? So it allows us that efficient exploration, and also allows us to then separate that out and define either random variables and propagate uncertainties later, or to conduct those kind of design questions. And in that case, we could then revert back to these univariate fragility functions, the more classic form that are shown on the image on the right, after integrating with those other random variables of at least the important predictors that were identified. Excuse me. So the examples that I've shown to this point build separate surrogate models for each of the key components. So for the columns and the bearings and the abutments, and compare and leverage different machine learning models for those. Some of the work that we have done more recently is looking at how we can build these single models, these multivariate surrogate demand models that will simultaneously predict the response of all of those components. And some of the purpose of that is, well, we're not having to go through the effort of training 6 or 8 different models for key components, but also it helps to preserve some of the physics of the problem and some of the correlated behavior of those components. And I'll hopefully highlight that for you in a moment. So on the left-hand side, you see kind of the classic approach that had been taken. So we have a structural system with multiple important components, and we see examples on the bottom for buildings. Perhaps we care about both structural and non-structural components. For the bridge example that I gave, we care about perhaps columns and bearings, things that contribute to different failure modes. And rather than separate demand models developed for each of them, we'll use a multivariate surrogate as illustrated on the right. And that was some of the work that Al Du, who's an assistant professor now at UT San Antonio, has done in some of his work, is comparing different systematic trend models and error covariance models. And that's really the key of some of this work, is that it allows us to avoid some of the assumptions or simplifications that we've made in the past in terms of the correlated responses of these components and the uncertain behavior about those component responses, and capture them more systematically. On the bottom right, you see an example from a publication that came out in Earthquake Spectra last year that we did with some colleagues at Sherbrooke University in Canada, looking at bridges, but typical of Quebec, but applying one specific example of a multivariate surrogate demand model, and that would be the Gaussian mixture model as one example. So this allows us to capture those correlated, say, bearing, abutment, column responses, but take care with that joint distribution as well. So what can these types of surrogates perhaps enable us now to explore and what features can we capture that perhaps we couldn't with our traditional approaches. One that I've tried to highlight up to this point is the fact that we can capture parameter variation so that we can have more tailored estimation of damage or failure probability across a whole portfolio of hundreds or thousands of structures. So the alternative to this perhaps is the extreme expense, although I think with machine learning we can get there, of constructing unique fragility functions for every structure in that portfolio of hundreds or thousands of bridges. The alternative might be what has been used in the past is we just have these archetype fragilities. We have 6 functions, and if you're a concrete multi-span bridge, you're going to get this function. If you're a steel girder bridge, you're going to get this function. And this allows, I think, a compromise in between for now, which is we may have separate surrogate models that have tailored predictors that we can apply across that portfolio. So every concrete bridge no longer has that same function applied to it, but it's tailored with those different predictors. What else might it afford us? One would be the opportunity to look at multi-hazard effects or joint load effects. The example on the left shows an exploration of how aging and time dependence can influence seismic fragility. This is actually a later study by Gosh and one of his students, but he started some of this work probably 5 years prior, looking at time-dependent fragilities and then very specific cases of corrosion and deterioration and how that influences seismic behavior, all afforded by some of these efficient surrogate models. On the right is an example of joint load effects. And so some of those questions of what if there are traffic on these structures when the earthquake hits? How does that influence seismic fragility? I mentioned multi-hazards, and this is a case of not concurrent load effects, but if we have these non-concurrent hazards, but a particular site, you may be interested in the trade-offs that you have in design details. So consider a location where we have the potential exposure to both earthquakes and hurricanes, maybe South Carolina or Puerto Rico. If we were to construct our parameterized fragilities enabled by those machine learning models on a common set of parameters, then we can look at how design variations in that common set influence our total risk across multiple hazards. One thing I'm really interested in exploring more deeply is this risk profile. So how much of our total annual say failure probability or annual losses may be contributed by exposure to hurricanes or earthquakes or other hazards. And if we were to change design parameters, now simultaneously understand how that influences risks to different events. So beyond some of the fragility examples that we focused on mostly today, I did want to acknowledge some of the other domains within the resilience quantification framework where we've leveraged some of these tools. And one particularly is looking at restoration of functionality after a damaging event. So first off, how would we even define the functionality of the system if we saw that combination of components that were damaged to our bearings and our columns and abutments? What are some of the subjective decisions that might be made in terms of closure or lane restriction or speed restriction? And then what are the recommendations for repair and restoration that are made after an event, and how long might that take? So we went upon an effort to collect some of this information from both empirical data that was available after past events, but primarily from seeking it from expert opinion through a web-based survey. And I'll say that this is an effort that we undertook about 20 years ago in a slightly different context, and I said I would never do it again. And we found ourselves doing it again because for a lot of these types of problems, it is that subjective decision-making that's really important if we want to be able to characterize consequences after the physical damage to our structures. So we went back to trying to understand those human subjective decisions. And then how do we parse that data set for kind of knowledge gain and predictive models? We used some of the tools that we saw this morning. We used decision trees for looking at models of closure decision. If you saw column cracking and you saw bearings that were damaged, then What likely decision might you make in terms of closure? So you can go down these interpretable trees now and see what the probability of closure is given some combination of component damages. We also, so that would be kind of your classic classification example, but on the right, then we were looking at duration, so more of the regression style, predicting the duration of closure given that the structure was closed. And in this case, we used random forest, that ensemble of decision trees for predicting the closure durations for different combinations of components. And this provided us the opportunity then to explore at a regional level the damage implications and the functionality implications over time of earthquake events. So I won't spend much time on it, but just quickly highlight how we integrated these types of models into a test bed application in the Memphis area. This is a part of a test bed that the NIST Center of Excellence has built. It's kind of built on some of the old Mid-America Earthquake Center work, if it looks familiar to some of you. So in this region, we looked at intermodal transportation systems, so bridges, roadways, railways, intermodal stations and junctions where goods are transferred across these networks. And we can now, by integrating some of these fragility models and restoration functions, look immediately after, say, a scenario event at the likelihood of damage and closure and the expected restoration over time with those restoration functions. Some of the insights that could be gleaned from this type of analysis would be which components dictate closure in the short and the long term. So we found in the long term, the closure is dictated by the bridges, the restoration of those structures, but the initial loss of functionality to this intermodal network was dictated by the terminals where goods transfer occurs across the systems. That only kind of looked at damage and functionality. These could be integrated into different types of network models. And I think we'll hear more about this in a later presentation today. I will say we did not leverage machine learning algorithms for the actual network simulations here. We use simpler models for this, but this might be another ripe opportunity where we could leverage machine learning is at the network performance scale. We looked at things like goods flow disruption and cost to ship goods through these damaged and disrupted networks. And we're currently working with Andres Gonzalez from OSU to look at restoration scheduling. So we're actually given a set of constraints. Should we be sending crews out after an event in order to restore, say, a particular route A to B in this network so that the goods will flow effectively? So this is still ongoing. Related, I think, opportunities that I wanted to leave you with. Since that 2020 paper, that review paper, I think there's been a lot of work that's actively using transfer learning as well as active learning in this domain. I think one exciting opportunity about the active learning concept is shown on the bottom of that left-hand figure, that there really is this feedback loop between, say, your sampling is referred to as the world here, but you're sampling, for example, and say the fragility or the resilience quantification and guiding smart sampling in this space. So the promise, the idea is at the right, that relative to, say, some random sampling or other efficient sampling strategy, that we can learn where we actually need new simulations to guide more accurate simulations of fragility or of, say, network performance. Another opportunity that I see is on the left, we see kind of this classic resilience curve and the potential for repeat events. And we hear a lot about Internet of Things and the smartening of our cities and systems, but how can we really leverage that streaming data to update these models? A lot of the models that I showed today are models that we build, we integrate them in an open source software, and frankly, we walk away from them. They aren't continuing to learn from streaming data that's coming from these systems, from field observations, from cameras and traffic sensors and other things. So to have that continuous loop would be another opportunity, and I think it's right for some of the AI and machine learning work. A last one that Raul is working on is leveraging some of these tools for efficient uncertainty quantification and propagation. We talked about all of these different nested models from the hazard all the way to network performance. And so this would be an opportunity to leverage some of the techniques, including some of the active learning that we talked about today. And then lastly, I think we have an opportunity to make that culture shift to really sharing data. We heard a little bit about design safe earlier today. In fact, some of the data that we use for testing and comparing those algorithms for the bridge response and the new probabilistic seismic demand models or meta models is there on design safe. But I think promoting that culture where we share these different data sets could allow us to test and develop new algorithms, but also to have kind of these learning and growing models as well. So with that, I want to thank my research group. This was a bit of a review of some of their work for the last 10 years, and happy to join the panel later.
Thanks, Jamie. Our next presentation is by Tamhidi with UCLA. The title of the presentation is Artificial Intelligence and Earthquake Engineering, Application for Seismic Performance of Soft Story Buildings. And Aiden, I think you are gonna present, so I'll stop sharing. I think you're gonna share your screen now.
Yes, thank you. So you can see my screen right now, right?
Yes.
Okay, great. So let me go to presentation mode. Okay. Hello, everyone. Thank you very much for the opportunity. I'm really glad to present our work in 4th Genji Ishihara Colloquium series. Today, I will talk about our developed workflow to estimate the seismic performance of soft story buildings using artificial intelligence. I wanted to first thank my collaborators, specifically Professor Bozorgnia, Dr. Nico Kuhn, and Dr. Mohammed Alipur. So with that, let's head into the introduction and motivations. So we know that there are lots of soft and weak story residential buildings, specifically within the West Coast cities. Basically, they have a large opening for parking or commercial spaces, and they are technically vulnerable to single-story mechanism, specifically for collapse during the medium to severe shakings. So, as an illustration, Los Angeles City detected and basically detected and mandated to retrofit about 13,000 of these soft story buildings within Los Angeles City. You may see the map of the distribution of the soft story buildings within the Los Angeles City. I have to just mention that this is within just Los Angeles City, so that Santa Monica, Inglewood, and other cities within the Los Angeles area is not shown here. So the traditional post-earthquake damage assessment of buildings generally is done visually by experts going and investigating the city and report the damaged buildings. As an illustration for 1984 Northridge earthquake, it took about like 2 months to finish these inspections. Therefore, rapid post-earthquake assessment would be essential. The main benefits will go to first responders, that they can efficiently allocate their resources, also to stakeholders, insurance companies, government agencies, and many more. But for real-time structural performance assessment, we need technically two main components. First is input ground motion time series, which will be the excitation for nonlinear response history analysis, and also a reliable structural model at the site-specific location.
Aiden?
So let's head into the ground motion simulation that we use to...
Aiden, sorry to interrupt you, but I think the slides stopped sharing.
Oh, really?
We are not seeing your slides. I'm sorry to interrupt you.
No worries. Let me... So can you see my slides now?
Yes, but it's not in presentation mode. It's in.
Yeah. Let me go back from previous slides.
Okay.
Okay.
There you go. We can see your slides now. Thank you.
Great. So let me just review what I shared during the past slide. So basically, the traditional method of post-earthquake damage assessment of the buildings is very time-consuming. It's technically done by visual inspections by the experts. For example, for Northridge earthquake, it took about 2 months. So a rapid post-earthquake assessment would be very beneficial and essential, and it would help first responder agencies to allocate their resources efficiently right after an earthquake. It would benefit the insurance companies, stakeholders, government agencies, and many more. But for a real-time structural performance assessment, we need 2 main components. First, the input ground motion time series at any target location, and second, a reliable structural model at that location. So we would be able to perform a nonlinear response history analysis at the location. We provided both components through machine learning algorithms and methodologies. So first, I will start with ground motion simulation methodology that we use. The number of available ground motion recording stations within the California is really sparse. So you may see the map of the recording stations that there are approximately 2,000 of them, meaning that there is just one station per each about 200 kilometers square. In the right map, you may see the shake map results of 2019 magnitude 7.1 Richter earthquake. And surprisingly, within the central region, we have like 6 stations within a 50 kilometer by 50 kilometer domain, meaning that one station per each 400 kilometers square. So that brings the issue of estimating the ground motion time series at the locations that there is no instruments, as we know that this is the key component for nonlinear response history analysis. Therefore, this brings the topic of condition simulation of ground motions, where you see you have given with a couple of observed recorded ground motions within a region, and now you want to know what would be your time series at the target location, in our case, a soft story building location. So we used Gaussian process regression model, which is a supervised learning machine learning model. To do so, we have decomposed the discrete Fourier transform coefficients of the recorded motions into real part and imaginary part. And previous studies have shown that these 2 variables could be assumed as Gaussian variables within a region. Therefore, our goal would be basically estimate the Fourier transform coefficients at the target location. So our problem is converted to having observation of real part or imaginary part at the surrounding locations at each frequency. What would be our target locations, DFT coefficients? So I would review quickly about Gaussian process regression. Basically, it uses a prior mean and covariance function for our target unknown function. We use Matern kernel function with nu equal 1.5, and the distance between 2 stations which will be fed into the covariance function is a normalized distance between the input vectors of the stations, and the theta that you may see here is basically the normalizing factor. So in general, in machine learning algorithms, the parameters of models is driven through maximizing the log likelihood of observations. We use maximum posterior estimates of the parameters, which will basically which will be an optimization problem through maximizing the Q theta, or the posterior distribution of observations. We have also introduced a regularization factor for this. We use basically a regularization factor for this function, as there are basically sparse observations generally in the recording motions. So this penalty function and its subsequently its regularization factor, or lambda, will be playing the role of hyperparameter of the model, which I'm going to show that how we set through the statistics-driven methods. So before that, we also used 4-component input vectors for each site for our simulation problem. So these 4 components include 3D Cartesian components of the stations on the surface of the Earth, and stacked with logarithmic VS30, which will be responsible for the site condition. So in other words, our all observed stations, as well as the target location, will have these 4-component input vectors. The whole procedure and the detail of the simulation can be found in our published Bulletin of Seismological Society of America paper, shown here for interested readers. So the regularization factor that I discussed in previous slides must be optimized, and this hyperparameter is sensitive to the density of the observations. As a case study, we use magnitude 7.1 Richter earthquake recorded at Community Seismic Network, which is a very dense network within Los Angeles, and it's operated by the collaboration of Caltech and UCLA. Here we use 252 recording sites within a 464 kilometers square. You may see that how the density is high, about 0.54 sites per each kilometer square. So we also use L2 penalty function. The function is given here, and we are aiming to basically find out the best lambda. So as we discussed, the regularization factor is sensitive to density of the observations. Here, density of the observed ground motions within a region. Therefore, we randomly sampled 6 different data sets of Community Seismic Network recorded motions and conducted leave-one-out cross-validation to match the ROT-D50 spectrum of the estimated motions at each location to the recorded one, and find out which lambda results into the lowest average error between matching the ROT-D50 spectra. So this is the table of the optimized lambda, and you may see that when the density decreases from 0.54 to 0.05, the requirement for penalty function or regularization is increased by having the lambda increased. So this is one example of our estimation for one station using the maximum density, using the lambda hat equal to 0.05. In this figure, we may see the estimated motions in black and recorded one in red, and the top row is showing the acceleration. We also will be able to generate any desired number of random realizations of ground motions given the output of Gaussian process regression, because Gaussian process regression is providing both mean as well as a standard deviation of the estimated discrete Fourier transform coefficients. So these are the acceleration at that location, velocity, and displacement. And you may see that how fairly close the estimation of Gaussian process is to the recorded one. Also, we have shown the Rodley 50 spectra of those realizations. Basically, these are 100 realizations. The left figure is showing the mean estimated one to the recorded one and the realizations, and the right one is showing the comparison of the 68% confidence interval, or let's say the mean plus minus one standard deviation, with respect to the average of the ground motion models estimated at that location and their within event standard deviation. So let's move to structural model development part. So that the part that I discussed so far was related to the first component for rapid post-earthquake assessment, which was the ground motion simulation at target sites. Now, for structural development for basically soft story buildings, previously 32 open-system structural models have been developed by Burton et al. In 2019. They basically generated these archetypical structural models after surveying the soft story buildings of Los Angeles. So their open-system models are generated based on 4 key parameters. The first one is first story wall layout, where they use 4 different patterns named L1 through L4, and you may see the examples of them below the schematic models. Also, number of stories, which the study shown that more than 95% of the surveyed buildings are either 2 or 3 stories. Therefore, their open-system models are for either 2 or 3 stories. They also considered 2 plan dimensions for each wall layout pattern. One is called short aspect ratio, and the other is longer aspect ratio. And you may see the dimensions of each of those plan dimensions for each wall layout pattern. And lastly, 2 different wall materials are considered either as gypsum wallboard or horizontal wood siding. So you may see that all these parameters lead to 32 OpenSys or structural model for the Los Angeles inventory of buildings. So our goal is to automate these these features detection for each soft story buildings within Los Angeles City as a test bed. And we used computer vision and image recognition methodologies to do that. So for that, we basically will we have used convolutional neural networks, and so this is the map that I showed at the very first slide. We basically used about 2,600 of the buildings as our training set buildings to harvest their images to train our convolutional neural network models, and we used 2 sets of test set. One is shown in the green, and this is basically used for image level performance evaluation of the model, and the yellow one for the application or building level performance evaluation, which I'm going to discuss later. So we use a Google Street View API, which is a static API that you may download the images given the coordinates of any target building. So for that, we use basically all locations within an 80-meter radius of neighborhood from any target building, and we interpolated at every 7 meter along the center line the streets. This is basically provided by the GIS coordinates of the center line buildings provided by Los Angeles City. And now we have to set up the camera location to capture the building's image from different locations. And you may see that, for example, for the east-west and north-south streets adjacent to the target building, we have almost 7 extracted points. And then the harvested images shown above for the east-west street, and also in the left-hand side for the north-south street. This is required because the opening part of the soft story buildings are not necessarily captured from the default coordinates of the buildings, which are shown with the green circles along the streets. But you may see that, for example, at the fifth and the sixth camera location along the north-south direction of the street, you may see the opening of the buildings. So we have harvested all these images, and then we labeled manually these images to provide the training data set for our model. After observing 2,600 buildings, we found that 87% of these Google Street View buildings, basically Google Street View can capture 87% of the buildings' images, but about like 30% is not able because sometimes the opening is in the backyard where the Google car cannot get access to capture the image. Also, the distribution of the pattern L1 through L4 were close to those that Berden et al. Reported in 2019. But we also introduced a fifth class. We call it as L0, where the pattern of the soft story is not fit into any of those L1 through L4. And also for the images where the image does not show any opening. For the number of story detection, also we found that about like 97% of the buildings are either 2 or 3 stories, and like 3% are 4 or 5 stories. So this is the distribution of the training set images. We may see that L2 was the minority class within our data set, but we also see that about like 5% of the buildings are fit into that class. So the test set, which will be used for image level performance evaluation, also is about like 360 images, and the distribution is shown. Similarly, for number of story detection, we use 2,300 for the training and test set of the images. We used basically various architectures, but we ended up with ResNet 152 model using TensorFlow data frame for training the model. And you may see the architecture of the neural network here, and the output of the architecture will be basically the probability of each class within this first story wall layout detection as well as number of story detection. So the first story wall layout tested accuracy was about 80.1%. You may see the confusion matrix of validation set and test set of our trained ResNet 152 model. Ideally, the diagonal elements have the maximum values, which means that the most accurate detection for each class happened correctly. These numbers that you may see in the confusion matrix is referred to recall because we normalize for each true label these values. The F1 score also of the classes are shown here. You may see that most of them has about like 80 plus percent of F1 square, except of L2 and L4. But L2 is also was one of the minority classes, so we don't see much of them in the in our data set. Also, we have mapped the class activation map through the GradCam methodology to know which part of each image made the model to predict the correct label. And I'm showing, for example, 4 examples of L1 through L4 classes, and we can see that the model technically was able to correctly detect the opening part of the first story for the truly classified buildings. Now we can see the number of stories tested accuracy, which is about 90+%. Again, the diagonal elements have the maximum values within the confusion matrix, and F1 scores show higher performance for two-story buildings, which was the majority class, and also about 8.83 for three-story buildings. This is the shown of true positive, and false positive examples of two-story, three-story detections of our model. So lastly, we have to come up with an algorithm to label a whole building using these harvested images. So what we did is basically for any target within the application buildings, we will compute the probability of either L0 through L4 of each image. If that image has the probability of more than 60%, we will label that image as L0. If it's not, we will label it as non-L0. Then we will calculate how many percent of buildings harvested images will be labeled as L0. If more than 85% of them are labeled as L0, we will label the whole building as L0, meaning that either we cannot fit the softest story pattern within those L1 through L4 classes, or the harvested images does not show the opening of the building. But if less than that is labeled as L0, we will basically take the take the average of the all images probability between each of L1 through L4 classes, and we'll pick the label as the maximum mean probability among those classes. Having that algorithm, we used application tested yellow buildings, about 120 buildings, to label them through harvested images through this algorithm. And then we also asked one of our interns to do same labeling to compare the model performance with the human performance level. We may see that the accuracy of the model performance was about 76%, whereas the human performance was about 84%. The confusion matrix of the model and human predictions are shown here. Similarly, we did the same thing for number of stories detection to compare the model performance with human performance. Lastly, so those were basically for the first two key parameters of the model. For the floor plan dimension, we have used the OpenStreetMap results, which basically provides the coordinates of the buildings, and we can get the area of the building. Then we use the closest floor plan dimension to the true area of the building, as basically softest story buildings will work with the density of the distribution of the shear walls within the floor plan dimension. So this will provide our third component. This is the performance of our model for another sets of 1,300 buildings other than the training and tested that we use. So you may see in the left figure that we have distribution of the prediction for L1 through L4 classes. As we expected, L1 and L3 had the majority of the type of the buildings. In the mid figure, we have detected the number of stories of the buildings, of soft story buildings. Also, as I just mentioned, the floor plan dimension can be estimated through matching the area to the closest structural model, which will provide 3 of those 4 key features. For the wood panel material, since the images can from like a street view or aerial images cannot provide the information about the material of the inside of the buildings, other data set can be used to match the wood panels material. So in the application at the end of our workflow, suppose we have a soft story buildings shown in the map. And also we have the distributed stations. Suppose this is coming to Seismic Network stations and California Integrated Seismic Network stations. Within Los Angeles, an earthquake happens in the Los Angeles, and our image recognition workflow can lead us to the closest structural model. Also, Gaussian process regression model will provide the whole time series at the site-specific location, and then combination will basically provide us with the nonlinear response history analysis of the structures, and ultimately we can define three level of performance. Let's say serviceability, capacity, and collapse initiation, and this will be repeated for many, like thousands of buildings. Suppose we have like 13,000 within Los Angeles, but many of these numerical analysis can be done quickly after an earthquake to map the level of performance of each building within a region. So let me wrap up with the conclusions and future works. Our goal was basically to carry out a near real-time seismic performance assessment of the structures. We simulated the ground motions using Gaussian process regression models at the target sites where there is no instrumentations. Also, we've developed the automated algorithm to given an address of a target building. We can get the visual characteristics through power of AI, especially image recognition, to match with the closest OpenSys model. So having the OpenSys models, or in general structural model, as well as the whole ground motion time series at the location, we could perform the nonlinear response history analysis, which ultimately generate the performance level of the buildings in a CDS scale. So we have seen that AI can be a powerful tool to be used in various applications, ground motion simulations, and basically structural feature detection through extracted images. So that was it, and thank you very much for your attention.
Okay, I'm going to get started with my presentation. Hello, everybody. I'm really excited to be here sharing with you some of the work that I've done during my doctoral work along with my advisor, Jack Baker. I actually just finished my dissertation last week, so I'm extra excited about sharing this work that we've been up to as finishing this stage. And it's very interesting how throughout the day we've seen different applications of artificial intelligence and machine learning into earthquake engineering. And today I'm going to share with you how we use deep learning methods, in particular neural networks, to enhance the seismic risk assessment of road networks, and also taking advantage of some explainable AI techniques. We did not only explore seismic risk assessment, but we also explore how we can inform decision makers to propose mitigation actions. As a motivation in general, we know that road networks are really important for our communities, as most of our daily activities depend on these critical infrastructure. Either going to work, to school, you got to see this presentation for those that are in person because you were able to take a road network that was functional. Also, these are essential to our communities because they use them to fulfill their essential needs by accessing goods. And also road networks are used by emergency services so they can respond to crises. However, while these systems are really important to our communities, they're also vulnerable to experience disruption. And we've seen that in the past, especially in California, after some earthquakes that we had in the 80s and the 90s. After the Loma Prieta earthquake of 1989 in the San Francisco Bay Area, we observed that the Bay Bridge that connects San Francisco and Oakland experienced the partial collapse of the upper deck, as shown in the picture on the left. And with this, the commute patterns were affected for months to come after the event. It generated huge delays, and which it's even farther than it was before the earthquake. On the right, we can see that 5 years after that, in Southern California and Northridge, some of the most shocking images we're getting out of the earthquake were the collapse of our critical infrastructure with bridges affecting commuters. And also, there were several studies that show that lack of accessibility also affected businesses and had broader economic impacts in the region. Luckily, it's not only us researchers that know that these systems are important, but actually decision makers and policymakers are aware that this critical infrastructure is essential for our communities, following what Professor Padgett was saying in the broader concept of resilience. The United Nations proposed this standard framework trying to provide guidelines for our governments to create and enable resilient communities. And they explicitly mentioned that regarding critical infrastructure, we need to, as a target, substantially decrease casualties, economic losses, and damage to critical infrastructure, such as road network, and consequently disruption of basic services associated with natural disasters. While this goal is valid, one of the main obstacles of what actually is not happening, according to the World Bank in their Lifeline books of 2018, is that one of the main challenges of why we're having issues increasing the resilience of our infrastructure is that we lack modeling tools to inform decision makers. And here is where I strongly believe there is a huge potential of using AI to inform decision makers. These systems that are highly interdependent, that comprise thousands of elements that are used by millions of people, and as Professor Padgett mentioned before, it can be even at a nationwide level. They are really complex, and analyzing them can be computationally expensive. And I think AI, with the use of surrogate models or other techniques, can be instrumental to find a way around this computational cost. And that's what I'm going to go as an example today of how we did that for road networks and community impacts. We did it with this in mind, of this objective of enhancing the resilience of our community, and in particular of our road network, given the role that this system plays. The objective of my doctoral work and the research we're doing at Stanford with Professor Baker has been how we can develop different tools so we can select bridges to retrofit, that is, preparedness actions, so we can minimize the impacts of road network disruption in a probabilistic manner. As shown here, we want to select what bridges should be intervened so we minimize the whole impacts of earthquakes in a seismic region such as the San Francisco Bay Area shown in the right. And speaking of, most of the AI techniques, and I want to briefly introduce our test bed here, is also San Francisco Bay Area, for which we have a model that comprises 33,000 road segments, 20 million trips per day. And in terms of managing actions and mitigation actions that we can take, we are working on improving 2,000 state-owned bridge by the Department of Transportation of California, Caltrans. And as I mentioned, it's not about scenario-based, but it's about pseudo-hazard consistent scenarios that represent the underlying seismicity of the region. And for that, we have a portfolio of almost 2,000 earthquake scenarios which unfold magnitude, extent, and of course, given this regional simulation, for each scenario, we have different realization of ground motion that account for a spatial correlation. With this in mind, the performance metric that we use in terms of aggregated or societal impact was a traffic performance metric that aggregates travel time for all users. And also, sometimes there is not only an increase in travel time, but it's actually this connection in the network. So we aggregate the travel time, and we also add the number of trips disconnected to have this whole metric of performance in units of time. With this in mind, as I mentioned, we want to inform and see how AI can be used for the seismic risk assessment of these systems to motivate mitigation actions for decision makers. So to motivate this, let's take a look at how we can assess the risk of these systems. So for a suite of hazard consistent scenarios, which I mentioned were up to 2,000 in the case of San Francisco Bay Area, here I'm showing the process for each scenario. And for each scenario, we start off by having characterizing seismic scenario through a ground shaking, which in this case, given that we're only looking at bridges, we'll look at how the spectral acceleration at the regional level was quantified using ground motion models. Then a second step using the formation of a seismic scenario and fragility function information for each bridge, we can obtain realizations of damage. And looking at all the realizations of damage, we can obtain a damage map, which is a damaged version of the road network. As a follow-up, given that you have a damaged network, commuters and users still need to commute. So a third step is to actually model how that commute will happen. That is, if you live in San Francisco and need to go to Oakland or San Jose, what route will take? That process is called traffic assignment, and basically models accounting for congestion, accounting for some decisions of the user, how they'll move around an area. And as a final step, we aggregate all this information of traffic assignment into an impact metric that we can use to make decisions, such as change in travel time, number of lost trips due to the disruption of the seismic event, or as I mentioned before, the one that we use in this study, which is a traffic performance matrix that aggregates both travel time and number of lost trips. Now, the main contribution of our work and kind of illustrating the potential of AI arises from thinking about the computational cost of modeling the system. And if you take a look at the steps that I just described, the seismic scenario is actually really fast to compute. It's just a ground motion model equation with a spectral correlation. So it takes a fraction of seconds to compute in any computer. Damage maps is also really fast to compute. It's just a realization of a probability function. However, when we think about the traffic assignment step, the most simple model that you could think about, because in our reality, the model we use accounts for congestion and updates travel time. But if you think about the most simple model possible, you need to think about what are the shortest path between all the regions and destinations. For the San Francisco Bay Area, the origins and destinations are 1,500. So all the sets of region destination, all the pairs, add up for more than 2 million. And this is for one seismic scenario. So for 2,000 seismic scenarios that are hazard consistent, for each of them, you need 2 million computations of shortest path, which add up to 8 billion computations in total. So of course, that process is really slow, and that can impede a deeper analysis on how we can assess the performance of proposed mitigation action on these systems. Motivated by that, we aim to use a surrogate model using neural networks to replace this step. So instead of running a traffic model to model how people would commute within the San Francisco Bay Area, it could be any region, we use a deep neural network that would directly take damage map as an input and then would output the traffic performance metric as an output. Specifically in terms of input, the input would be for each bridge, we have a binary variable indicating whether or not the bridge was damaged or available. Just to clarify damage, we mean consider severe or complete damage for our analysis. So we have an input that is for each bridge, a binary indicator to whether or not it's available after the earthquake. Then we have a fully connected neural network with different hyperparameters that we calibrated. And then the output would be directly the traffic performance metric. And with that, we'd reduce the computational times for one seismic scenario from several hours to fractions of seconds. Given these inputs and outputs, there are different challenges that are underneath or under the hood of how we actually can train and validate this neural network. And is that at the end of the day, while we are taking advantage of all the development that people and data scientists have done in AI and machine learning, at the end of the day, we're still engineers and we're thinking about the resilience of our communities. So it's really important when thinking about deployment, not to think about these tools as black boxes or just packages that exist online, but actually questioning how we can use this tool for our purposes. How can we satisfy that the results of our models are valid? So some of the questions in that context that we formulated are first, how we account for extreme events. We know that there are some events that have a really low probability of occurrence, but have a huge effect on our communities. So how do you account that in terms of the sampling for the training of the surrogate model? A second challenge, which I'm not going to explore deeper today, is definition hyperparameters that is common to any other surrogate model you want to develop. But the third challenge that goes into what I was saying is how do we validate and how are we happy with the results that our surrogate model is displaying? And while, of course, you have this statistic metric of good of fitness, we also need to think about, we need to quantify and inform decision makers in terms of risk. So we need also to verify that our surrogate model is predicting engineering parameters in a good way. Today, I want to walk you through the first and the third challenges that are more contingent to what bring us today in the applications of AI into civil engineering. Keeping that in mind, the first question was, how do we train the model? What data do we need to generate for such a model that is balanced towards risk? The first thought that we had was, okay, all the analysis that we're having, we have a suite of hazard consistent scenarios. So we went ahead and sampled our neural network with visualizations of damage that came from a hazard consistent sampling, which means that it represented the seismicity of a region. And we observed that at a global level, it actually performs really well. But then when you look at how the bias of this model changes according to different magnitudes of events, we observed that there was a bias for extreme events, which made sense because when you're thinking about hazard consistent sampling, you don't have a lot of events that are highly disruptive because the probability of occurrence, thereof, the probability of being sampled is small. So keeping this in mind, we tried different bias correction techniques, and we ended up using a really simple one, which is if you want to tune better for a specific subset of your test set, then include more of that data into your training data. So here I'm showing the x-axis, the fraction of training data corresponding to extreme events, and in the y-axis, I'm showing the metric of performance, and also the curves show whether the performance of the model for extreme events, shown in blue, and in gray for all the events. And we observed that after 60% of the data is extreme, the performance on those types of events starts increasing significantly. Up to this sweet spot of 80%, where both all the events are not event extreme test data and all the extreme events perform adequately according to the neural network. This makes sense that you need to oversample these extreme events, because what triggers an extreme event? An extreme event, which is a highly disruptive event, has a lot of disruption, has a lot of damage bridges. So in terms of the neural network, having a lot of damage bridges is good because it's able to learn how the different components interact. And with that learning process, is getting better at predicting the value of the disruption associated by these extreme events as well. With this in mind, moving forward, all the results that I'm going to show have these 80% of extreme events, which is way higher than the 5 to 6% of the hazard consistent proportion that they are. As I mentioned, the third challenge that we wanted to account for was engineering parameters and validating our neural network in that context. So the first engineering parameters, when you think of risk, is we need to verify that our model is able to predict loss curves. So here I'm showing in a plot, in a continuous line, showing the results of using the traffic model, and in a dashed line, the results of using the neural network for different number of retrofitted bridges. And we observe that basically the lines are the same, but actually they are not, and they're not in a good way. And the good way is that each curve for in my own computer, which is the MacBook Pro of 2021, takes 8 hours, but the neural network takes 0.3 seconds to run, which is almost 100,000 times faster. And this is really powerful. As I introduced, the objective of my PhD was to explore retrofitting actions, which is something that the shoemaker can do. If you need to propose a strategy, in the past, you needed to run the traffic model, take 8 hours for each curve. But here, having trained in your network before, you have the neural network that takes fractional seconds, and you can explore way more retrofitting strategies or policies and see how that has a broader community impact. I'm going to talk later a little bit about how much data you actually need to train your network, which is something that, of course, is a question that arises as the upfront cost of training this model. Besides loss curves, of course, we need to, in terms of informing in a probabilistic setting, we need to be able to predict the expected error loss associated to one or other model. And here we can observe the y-axis, the performance of the neural network predictions, and the x-axis using the real traffic model. And they're basically the same regardless of where in the model we are. So that makes us comfortable about how the prediction of the neural network can be used to actually inform the seismic risk assessment of complex systems such as road networks. As I mentioned before, there are some data needs to actually train neural networks. And here I'm showing the performance of R-square value, which is accuracy in terms of number of realization in the training data. And we can observe that after 10,000 to 20,000, the performance becomes stable. So that's really encouraging because, as I mentioned, one suite of hazard consistent scenarios is 2,000 scenarios. So 10,000 data points is 5 evaluations of retrofitting policies. So what I'm saying here is that, yes, you need to generate training data to calibrate your neural network. But what I'm also saying is, in our case, within region and with this traffic model, again, this could change depending on the region and the traffic model. But here you only need 5 evaluations to afterwards just use your network instead of your traffic model, which is encouraging because it's not such a high data need. With that in mind, we are happy satisfied because we had a neural network that was fast, that accurately predicted road network disruption in terms of statistic validation, also loss curves, expected value, and it required reasonable data to be trained. But as I mentioned, it's not about being a black box. It's about understanding what's going on behind the scenes. So given this trained neural network, we started exploring different explainable AI techniques to try to gather some intuition of what was going on under the hood. And in particular, these explainable AI, what they do, they try to relate how the inputs of the neural network relate to the output with different weights and so on. And in our case, our inputs are the bridge damage states, and the output is the network performance. So you think that way, if we explain the neural network, we will explain how the damage of some bridges relates with the network performance, the road network performance, just to clarify, non-neural network performance. And motivated by this, we implemented the local interpretable model agnostic explanation model, and we actually proposed a new variable importance algorithm that modifies this line algorithm. Just to provide some intuition, this method is more complex of what I'm going to explain today, but I'm explaining some intuition so you can understand what we propose as a modification. This local regression model, what it does is that it explains individual realizations. So in the y-axis, you have the performance of the value of the regression you want to explain. The x-axis, you have one variable. Of course, you have to do this for all variables. And then let's say that you have trained a neural network that predicts accurately how the data can be predicted according to the variables. And then let's say that you want to explain an individual realization shown here with an arrow. What this method does is that it performs a local regression with a local surrogate model around the explanation that you're trying to explain, and then it goes back and explain and understands for this individual realization, the weight of each variable is as follows, and then it anchors the weight to the variable, with a variable having a higher weight being higher importance for that individual realization in terms of explainability of what was driven this realization of damage, for instance. With this in mind, something that we started thinking and we modified was that we don't want to only explain realization of damage, but we actually want to understand as a model what bridges in the probabilistic setting are more important than the others. So we propose a line TI algorithm. TI stands for traffic impacts, in which we need only explain individual realizations, but we explain the whole model in a probabilistic setting. So instead of having just one realization, we have realization with a specific rate of occurrence. We have another one, and then we explain each variable as the weighted sum of the probability of occurrence of the individual event with a coefficient that we modify respect to the coefficient that I showed before that comes from the original paper. So this coefficient that we modified, we call it line TI, that depends on the way that I showed in the previous slide. And with this, we can rank the bridge importance, but in reality, this is a generalizable explainable AI technique in which you're trying to understand a model that underlyingly has this probability distribution in the sampling of the model. With this in mind, these coefficients, just to provide a little bit more of insights, is that the value of that coefficient was obtained the following way. We first rank each bridge for individual realization according to the regional line coefficient that I showed before, that is the weight of the regression performed locally. Here, I'm illustrating 3 bridges, and then the value of the coefficient is according to the weight. So B2, of course, the biggest font, so this is the most important bridge, and then B1 is the least important bridge or input according to the regional line algorithm. So to incorporate the consequences at the transportation level or regression level, what we did was that we computed the coefficient of B2 in the following way. We compared the marginal detriment in traffic performance given that the bridge 2 was damaged. And we did that increasingly for each bridge to compute that coefficient. So after V2, the most important bridge is B3. So the coefficient of B3 would be the additional change when we damage bridge 3, given that bridge 2 was damaged. And so on. For B1, that is the last one, the contribution or the importance of that bridge is that the change of the availability of bridge 1 after we have damaged bridge 2 and 3. And so on when you have a different amount of bridges. So with this, you have a coefficient that is not only a local regression in general, but is a local regression that tries to quantify the marginal contribution of the bridge, given that the rest of the bridges have been damaged. And with that in mind, we have a ranking of the bridges according to their importance, a probabilistic setting. And we can use that to inform decision makers and think about how we can rank bridges and retrofit them. And here we verify, we're comparing to ranking bridges by their vulnerability or their traffic importance, as in how by damaging one bridge at a time. And we observe that ranking bridges, comparing to not doing anything, it's way better than ranking it by traffic importance or vulnerability. What is reassurance in terms of the strategy used? As I mentioned, we want to think about the intuition and think about how we can further explore and explain the solution of this algorithm. So besides ranking them, we are trying in our test bed, the San Francisco Bay Area, we try to understand some intuition of why the bridges selected by Lime TI were selected. And we realized that the Lime TI select bridges that are vulnerable. That means that can collapse more easily, but they're not that important, but they lead to important bridges. So for instance, in the San Francisco Bay Area, those who are familiar, the Golden Gate Bridge, the iconic landmark, is a really important bridge locally. And there are some bridges that lead to that bridge that are vulnerable. And these bridges should be retrofitted. The same happened with the Bay Bridge. So that's interesting because if you were to select bridges, you would not think about minor bridges, but in reality, you need to think about bridges as sets of or groups that work together. This bridge is needed by the big bridge, the major bridge, and so on. So we actually explored that in another paper where we actually use corridors to define these groups of bridges. As a further explanation, we actually tried to explore intuitive trends in the analysis, and we observed that line TI selects bridges with high individual contributions to changes in expected traffic interruption. Finally, as conclusions of this study, first, we verified that neural networks can accurately and rapidly predict traffic disruption in a large transportation model, given the damage state of bridges. Also, and importantly, in the concept of risk setting, when training the model, it is necessary to oversample extreme events, which have a large travel time impacts, because otherwise the neural network will focus on fitting frequent and small disruption events that are of lesser interest for risk management. As a third conclusion, we observed how explainable AI can be used to understand the surrogate model and also propose action to mitigate seismic risk in this case, which thinking about our applications, we think about soft stories, or we're thinking about restoration, as the previous presenter was thinking, if you were able to explain what variables are more important for the analysis, then you could also think about, we need to retrofit or we need to repair those elements first because they're driving the performance of the system. And then as a final conclusion that is not in this slide, but I think it's important to highlight, is that when analyzing these complex systems, there's a lot of research that has been spent on selecting seismic scenario in a smart way, because there is a lot of computational cost associated to individual realizations. But the use of AI in this surrogate model presents an alternative in which instead of selecting or a subset of seismic scenario, we use all of them. But instead of computing the original performance of the system, we use a surrogate model that waives or bypasses the computational cost of individualization. And with that, I conclude my presentation. If you have any further questions, we're going to discuss later, but you feel free to reach out to my email showed in this screen, or to refer to the article where we talk about this study showed in this slide at the bottom. Thank you.
Thank you, Rodrigo. We're going to start the questions part of the presentation of session 2. Any questions from the audience?
Thank you. I have a quick question for the second presenter, Aiden. Can you comment on what happens if the address is not available? Is there workaround for the cities that hasn't done the inventory for the soft stories? And then also based on your inventory, based on your evaluation, is the research in City of LA also scalable to other jurisdictions when they are not dense of a community seismic network, or the configuration of the soft story might be different? So
I'm so sorry. Can you repeat one more time your question? I just lost your first few seconds of your question.
Yeah, the first question is, I understand that what happens if you don't have the addresses of the soft story? So is there any workaround in your workflow? And then the second question is your research also scalable to other jurisdictions that without CSN network or other soft story configuration are similar? Thank you.
Right. Thank you very much. Thank you. So actually, we developed this methodology for soft story buildings because we have been provided with an inventory of structural models for soft story buildings. This could, I think, be broadened for other types of residential buildings or any inventory of buildings that we could do a survey and provide with various types of structural models given key features. So for our case, if we basically evaluated our model just on the detected soft story buildings for Los Angeles City, which the address of them is provided by Los Angeles City in 2016, which was about 13,500 buildings. Obviously, this could be also broadened for other cities as well. Regarding your second question, within the Los Angeles, we have basically this community seismic network model, which is a very dense network that roughly the distance of the stations are about 500 to 600 meters, which basically increase the accuracy of the simulated motions at uninstrumented sites. This could be also used for more coarse networks like CISN at different locations, like in Bay Area or like, let's say in Pacific Northwest. However, since the instrumentation density are getting increased by the time, ultimately we will reach out to basically a situation that most of the major cities have a really dense network. So this methodology can basically implemented to do rapid generation of ground motion times at uninstrumented sites.
So this question for Professor Padgett. You were modeling like interaction of multiple components. How do you validate or show that that's the interaction that happens, or how can you eliminate all the other possibilities if you're observing real data?
Right. So I think there's probably different stages of the talk where I mentioned the interaction of components. One was when we were looking at the structural system scale and we were looking at component interactions, which frankly is difficult, but a little easier than when we were looking at the regional scale and we were looking at interaction of components. From that standpoint, in terms of both finite element model validation and then looking at training some meta model, we had the beauty in some cases of damage observations at the structural system scale, whether it be from real events or from laboratory testing that we try to leverage. I think it becomes hard to say that we're truly validating our model with those. I would say it's more of a sanity check, because we're trying to validate probabilistic models with realizations. That's one stage. I think when we're talking about the full chaining, though, and some of the work that Raul is doing right now is where this is going to become more challenging. When we're saying we want to get all the way from looking at the hazard simulation to the damage to the propagation of uncertainty all the way to network performance, kind of like the challenges I'm sure that Rodrigo is facing as well. I think in that stage, we're still stuck with breaking down the problem and validating some of the individual pieces of the model, as opposed to having great data to validate the integrated chain effort. I think that's something our resilience modeling community is struggling with right now.
Just an extension to that, like, were you mostly interpolating within your data set, or the data publications are extrapolating outside of your data set?
Yeah. So the question for the audience online was, are we mostly interpolating within our data set, or are we trying to extend the models and apply outside? I think the existing examples that I showed here today, we're mostly constraining it to applying it also within the ranges that the models have been validated. I think there are some opportunities that I mentioned, some of the looking at transfer learning strategies and things of that nature that might open the door for us to start to apply them outside a bit more. I've been a little hesitant of that at this point. Yeah.
Since I have Jamie here, I had a question for her on, from my perspective of an engineer that works with buildings, you or any in your team working on surrogate models for building structures like older concrete buildings, etc.
So in terms of the probabilistic seismic response analysis of buildings is not something that we have been actively pursuing, but we are working with some collaborators from Italy to look at that functionality piece. So the two examples I showed were either the fragility and damage modeling, or kind of flagging and tagging buildings for functionality status afterwards and looking at restoration. And that's proven a really interesting study because there actually is pretty rich data much richer actually than I expected in terms of the flagging and tagging of buildings, of their usability or occupancy, and then some of the information on time to restoration. So we're taking some of the concepts that I showed for the bridges with the decision trees and the random forest for looking at restoration and closure models and applying them in the building context, particularly for reinforced concrete buildings and masonry buildings, but they're more typical of Italian construction. But I do think that the methods are portable to other systems. And it's uncovered some interesting insights, I think, in terms of, looking at different characteristic lateral force resisting systems and when we tend to see more conservative, say, flagging of buildings when there are fewer damage observations. And so that, I think it raises some questions about the transferability in some cases of models. Since I'm up here, can I ask a question? All right, I have the mic, so I'm going to ask some questions as well. Some interesting talks from our other presenters. I have one for each of you, but maybe I'll start with Aiden, and if there's time, then I'll ask for Rodrigo, but we'll pause. So Aiden, I really liked how you showed that you're going all the way from leveraging the sensor data from looking at hazards to machine learning or AI methods for identifying structural characteristics so that you can map a model, like a finite element model, to that structure. And I don't know if this question is more appropriate for you or for Henry or other collaborators, but I'm trying to think of how in this kind of active real world setting, we might try to deal with some of the uncertainties in this problem. So when you map, say, your building classification directly to a structural model, perhaps we might want to do more than just one forward simulation of that structure. Do you think that's feasible, or what other techniques might be needed so that we can start to acknowledge some of those uncertainties?
Thank you very much. That's a really good question. So yes, absolutely. Basically, I think the uncertainty of the final estimated performance of the buildings can come from actually both components. One from what's the uncertainty of the input excitations, which we've implemented random realizations of ground motions at the site-specific location through our Gaussian process regression. So therefore, the end user will not have just one estimated motions, but also, like, let's say 100 realizations, and they can incorporate all of them to do different or numerous nonlinear response history analysis. Also, for the uncertainty of the building structural models, let's say other than the because those OpenSys models are developed for after surveying a portion of the buildings. But in our work, the ultimate output of our neural network models are basically probability of allocation of each building to each of those classes. So suppose that we label the building based on the maximum probability among all classes, but still there are some minor or other probabilities that a building is assigned to other labels too. So suppose we can basically generate other nonlinear response history analysis given those other for other types of buildings, and then combine all of them, collaborating or incorporating the probability of each class, either for the soft story type or the number of stories or other things. So combination of those probability and combining those uncertainty of those models versus with the input motions can basically generate numerous nonlinear response history analysis at the end. I hope I got close to your question.
Yeah, thank you so much, Aiden. Very helpful.
Sure.
I had one for Rodrigo, if we have time then still. Rodrigo, thank you for showing the example of where you would leverage machine learning at the network scale, which I agree is probably the more computationally challenging piece, where the argument may be stronger in this case. going through that process, I was curious if you tackled the challenge of kind of the post-event demand modeling side for like the traffic flow modeling. That's something that I'm always struggling with and hesitant to know how to truly compare the flow pre and post events if we don't have good data on the origin destination matrix changes and things like that. So were you able to tackle that, or are you making an assumption of same as before?
So that's a really good question, and I'm glad that I'm not the only one having a hard time sleeping with the changes in OD, because it's really challenging, and it's weird to give a recommendation on what to do if you're just accounting for the immediate disruption, if you don't account for recovery or restoration. So to answer your question, for the neural network that I show here, I assume that the OD was constant, as you were saying. But we've been looking into first answering, there are two questions that need to be solved. First, how do we change the origin destination matrix given damage and interaction of the built environment and the road network? And the second question is that, okay, but you still have the problems of computational cost, right? So then how do you develop a surrogate model that accounts for those changes in the origin destination? So to answer the first question, along with other collaborators within Stanford, Gitanjali Bhattacharjee and Alan Poulos, we've been trying to link building recovery along with road network damage and recovery, with taking into account that there is a lot of research that needs to be done with the recovery curves that we know that right now there's a lot of information for leading curves, but not on recovery. And basically, we're saying that if the destination was damaged in terms of workplaces, then we're taking that information out of the origin destination. Right now, we're looking just at destination. We're thinking maybe we have some information about residences. We can also model that. But that is the first approach we're taking to origin destination, and we're running some experiments to prove that. And regarding the second question, the ability of the surrogate model, what we're thinking about is, so in terms of origin destination data, we have different levels of aggregation of the origin destination data. One is census tract level, the other one is city level. So at census tract level in the Bay Area, as I mentioned, we have 1,500. At a city level in the Bay Area, it's 35 origins and destinations. Initially, what we thought of a surrogate model was directly take the input of the drop in demand as an input to the neural network, but then having all of those on top of the damage require a lot of data. So what we're thinking is, once we see how the origin and destination changes, once we incorporate building damage, we're thinking about incorporating as features of the surrogate model, but at aggregated level. So in this case, it would be not 1,500, but it would be 35. So at city level demand, and then see how much data will basically retrain what I showed today, accounting for that changes the origin destination. So we're using recovery. So if you have embedded information about recovery models or restoration curves for bridges, that would be great, because that has been a ton of source of discussion of what restoration model is the one we trust the most so far.
Yeah, I agree. Big challenge. One opportunity that you might have, you mentioned how you would consider the destination change because of the damaged buildings. And I love that idea that you're already headed that way. Maybe on the origin side, if there are population dislocation models that you can use. I'm actually not quite sure if they're good ones post-earthquake. There are some interesting ones I've seen coming out post-hurricane and flood, when people are likely to leave and how long they'll stay gone. But that might be the other missing piece of the OD matrix.
Yeah, I think that... Thanks for sharing. Yeah, and another challenge, and in this regard, is given when they go recovery versus restoration curves, is that if you are displaced from if it's hard to get from your job for 8 months, it's not like you're going to keep that job, but you're actually going to change. So actually, those shifts in the job market are really hard to model. So that's also another space for improvement.
I have one more question, since we have 4 minutes for Aiden. Since you're working with this huge database and knowing that now there's this ordinance in LA, have you guys thought of using maybe or introducing some of the strengthening procedures in the surrogate models, like a type, I don't know, 5, for example, and seeing the impact of that as, you know, the strengthening goes along?
So, if I understood your question, you mean incorporating the deep learning methodology for improving the structural models?
For adding the buildings that are strengthened through the City of LA ordinance.
I see. Yeah. So in our work, we didn't incorporate basically any retrofit through the or LA ordinance or other like design code or procedures, but we use just our methodology on for existing soft story buildings. But I believe that Professor Burton group also did some work and estimations for effect of the retrofit of the buildings on reduction of the loss estimation and damage of the buildings after an earthquake. So what we did basically was just trying to capture the key features for structural models for a given inventory of the buildings. But this also this computer vision and image recognition could also leverage to detect the other features to generate more various types of structural models, for example, for different types of buildings or number of stories or floor plan dimensions. Regarding the retrofit part, we didn't do that because we just considered the existing soft story buildings before retrofit.
Thanks to all the speakers. Thanks to Jamie, Aidan, and Rodrigo. And I think we're right on time. So right now we're going to have a break for lunch. And we'll be back at 1:30.